Hey friends, welcome back. It is the final lesson of the year. Can you imagine that? Holy cow, has this gone by fast. Now, in the background, you might hear my kids screaming because they are going crazy. Depends when you're watching this, but if you didn't know, I'm filming all these during the COVID-19 outbreak. So it's been a bit of an interesting learning curve here for me as we've been doing this. Hopefully, when you're watching this, we actually see each other face to face still. Okay, so if you are my current kids during the outbreak, geez, I miss you more than you'll ever know. This has been tough doing all these online. If you're one of my current kids who's not during the outbreak, hey, I hope I see you tomorrow. That'd be amazing. Okay, friends, here we go. Let's do our final lesson of the year. So we're going to do our final lesson of the year, which is called mutually exclusive, non-mutually exclusive events. Now here's our table again that I said that we would look at one more time with our two dice, and you were to fill this in one time. But this time what I'm asking you to do is we're actually going to find the sum of the two die. So all we got to do is just go through and plop in the numbers that we're going to get by adding these things together, just like that. Okay, so maybe hit pause because I don't know how exciting it is watching me fill this in for you. Hit pause and come on back, and then this will all be ready for you. Okay, you're back. You filled in the table. Nothing too difficult, hey? Adding things together. Now, the questions that we are being asked this time, it says, the first one says, let's find all of the outcomes that give us a sum of 5. Okay, so a sum of 5. I'm just going to go and let's put a heart on top of those because hearts are pretty. 1, 2, 3, 4. So 4, oops, I still got my hearts on. 4 out of 36. And I get that I could simplify that down, but I'm not going to right now. Sum of 10. Okay, what do I want to put on the sum of 10s? Let's go for our sum of 10. 1, 2, 3. So 3 out of 36, which again, I understand I could simplify, but I'm choosing not to because I'm crazy like that. And now our final question underneath says, what's the probability that we get a sum of 5 or 10? Okay, well, I'm just going to add these two things together, correct? So that would be 4 over 36 plus 3 over 36. So I get 7 over 36. And do you see why maybe right there why I didn't simplify down those fractions? Because when I'm adding, it makes my life a little bit easier. Okay, hey, that was easy. Last lesson of the year, that was pretty easy. Nice. Okay. Now what we're going to do is we're going to go on to the next few questions. And the next one starts off the same. It says, find, well, let's answer this question here. Is there any relationship between the probabilities for the sum of 5, the sum of 10, and the sum of 5 or 10? Well, really what I'm asking you is, can these two things happen at the same time? Answer is no, sir, no. They can't happen at the same time. If I was to think of a Venn diagram here, what this was going to look like is, here's my universe. There's me getting a sum of 5. There's me getting a sum of 10. Can they happen at the same time? Nope. So remember a couple of units ago, we would have called this disjoint. Now, let's take a look at the next question. Let's place a triangle over place a triangle over any sum that was determined by rolling doubles. Okay. Well, you go back up and do that. It's not a super difficult thing to do. Well, a sum of 10, we already know. That's 3 over 36. Rolling doubles, I know there's 6 ways to get a double. But now I cannot simply just add these two things together. This does not equal these two things. I know just by looking at the diagram and where you put all your little marks is I know the actual answer is 8 out of 36. So the question is, why doesn't it work for this example, but it worked for the other example? Because I know the word in math or implies that I should be adding. So why didn't adding these two things work here? I know the answer is 8 out of 36, but 6 over 36 plus 3 over 36 gives me the wrong answer. Why? Well, let's go back to Venn diagrams and set theory. If I think about these two sets, well, there's me getting the sums of 10. Here's me getting a sum or rolling doubles. What do you notice about those two sets? They've got an overlap right here. They're not disjoint, they have an intersection. What's in here? Well, that would be me rolling 2 5s. That would be me rolling 2 5s. So that's me getting a sum of 10 and doubles. So they're not disjoint. So when we're not disjoint, we're going to have to come up with a different formula, because when we're not disjoint, guess what? We can't simply just add those two things together. Okay, well, good news is this is rather easy to sort out. Other good news is it's on my formula sheet. So when two events, like getting a sum of 5 or a sum of 10, cannot occur at the same time, in the past we called this disjoint. But in this unit, because we're talking about probability, they define that as mutually exclusive. But I want you to keep thinking it's also known as disjoint. So if I want to find the probability of A or B, or remember there's our symbol, union, adding these things together, if they can't happen at the same time, I just simply add those together, because set A and set B are disjoint. If two events can happen at the same time, these events are called not or non-mutually exclusive. I'm going to be lazy here. I'm just going to write ME, not ME. So in this case, we can't add these together because there's an intersection. So what we're going to do, if I draw my little tiny, teeny, weeny Venn diagram here, my problem is if I just added them together, I'd be counting this area right there twice. Well, what is that area? P, A, and B. So I'm going to subtract it out. Or if I use my symbol, there it is. So when something's not mutually exclusive or not disjoint, we're just going to subtract out that intersection. Easy. Some easy idea. There they are right there, nice and pretty for you to see as Venn diagrams. Now, most of the time, we probably don't need a formula, but again, it's on my formula sheet and it's nice to write out. When I'm in a really tricky question, it probably get me out of a jam. So Here's my experiment, rolling 2 dice. The event is doubles or a sum of 3. So, are these mutually exclusive or not? Can they happen at the same time? These cannot happen at the same time. So this is mutually exclusive. No can happen same time. Just like that. Okay, what I want you to do is I want you to hit pause and check out the next two. I want you to tell me, do you think these are mutually exclusive or not? I'll see you in a minute. Okay, amigos, you're back. You tried these. Let's see how you did. Drawing a card from a deck. Card is red or 4. Well, that should be not mutually exclusive. Why? Well, they call it the 4 of hearts or the 4 of diamonds. So if it's not mutually exclusive, you should be able to give me an example of why it's not. Where's the overlap? Okay, last one. A student, class of 30 students in which 15 have cell phones and 22 have MP3 players. Okay, there was a time when these two things were separate and we would walk around with two different things in our pocket, but not these days. These days, we just call it an iPhone, right? It's the same thing. Easy peasy. So not mutually exclusive because they can occur at the same time. Okay, let's keep going with this. So in a class of 30 students, 10 are brunette, 15 are blonde, 5 are redheads. Okay, and we're going natural here. We're not talking about putting big crazy stripes in our hair or whatever. There's always one kid in the class who puts up their hand and says, well, I could have 25 different colors of hair. I'm like, yeah, I get it. Okay, just play along with the game. We're talking natural. So determine the probability of a student having brunette or red hair. Well, it never hurts to maybe think, is this mutually exclusive or not? Can I have both? Well, we'll play along with the idea that no, I can't. These are mutually exclusive. If I was thinking of it, here's brunette, here's red. I can't have both. They're mutually exclusive, which means then probability of brunette or red is equal to the probability of being a brunette plus the probability of being a redhead. So probability of being a brunette is 10 out of 30. Probability of being a redhead is 5 out of 30. And what's the probability of me selecting one or the other? Well, 15 out of 30 or 1/2. Now, always asking myself, mutually exclusive, not mutually exclusive. Are these things disjoint or not? Using a regular deck of cards, what is the probability of drawing a king or an ace? Are these mutually exclusive or not? Well, am I able to get a king and an ace on one card? Can they happen at the same time? No, they can't. So if I'm talking about the probability of getting a king or the probability of getting an ace, since they're mutually exclusive, I can simply add these things together. Probability of getting a king, well, I know there's 4 out of 52, and ace 4 out of 52, so that's 8 out of 52, which is 4 out of 26, which is 2 out of. Hey, just for giggles, we haven't talked about it in a while. What's the odds then that I get a king or an ace? Well, odds would be 2 to 11. Just in case. It's been a little while, so if this is the last lesson, we should be tying everything together. You probably have a test coming up. All right. In the experiment of drawing 2 cards from a deck with replacement, so hey, now I know they're independent. Determine the probability both cards are red or both are black. Okay, so I want the probability of red and red, or I want black and black. All right. Well, these are also mutually exclusive events, aren't they? So since they're mutually exclusive, I'm going to break it up into its respective parts. That's probability of red and red plus the probability of black and black. So they're mutually exclusive, so I can do that. But then because they're independent, I can now do this. Probability of red and the probability of red plus the probability of black and the probability of black, which is equal to, well, the probability I get a red card at any given time is a half times a half, plus the probability I get a black card at any time is a half times a half. And if you need to, you pick up your calculator, but that's going to be a quarter plus a quarter, which the kids tell me is 1/2. So you see there, we looked at this in 2 different ways, or at least I did. And then that's what you're going to do too, is I said to myself, this is mutually exclusive, and I said it's independent. That's going to affect how I'm going to answer my questions. I like it. I also like writing sentences out like this, math sentences, so that the person who's reading your work knows what you're doing. I can't stress that enough. Marking the diploma and getting these questions was incredibly frustrating because kids are just throwing numbers down all over the page. And we have no idea what they're talking about. Okay, what do we got here? The Lancers and the Chiefs are playing a best-of-5 series, so 3 games to win. Probability the Lancers will win any game is 62%. Determine the probability that they win the series, Lancers or Chief, in 3 games. Okay, so these are independent events and are also mutually exclusive because I can't have both things happen at the same time. So what this is saying to me then is I've got either the Lancers win all 3, so Lancers win and the Lancers win and the Lancers win, or I've got Chiefs win and the Chiefs win and the Chiefs win. Okay, so since this is mutually exclusive, I can break this up, and it's also independent, so I'm going to do this in one step this time. The probability the Lancers win, the probability the Lancers win, the probability the Lancers win, or plus the probability the Chiefs win, probability the Chiefs win, probability the Chiefs win. So what's the probability the Lancers win? Well, it says the Lancers will win any game is 62%, so 0.62, 0.62, 0.62. The probability the Chiefs win? Well, if the Lancers win 62% of the time, guess what? The Chiefs are going to win 38% of the time because there's no ties here. Boom. And now all we've got to do is put this bad boy into our calculator, and we're going to get some small number. Well, I don't know how small it'll be. I'm guessing around 20%. Just a guess. Hey, not bad. 30%. 0.2932. There it is. So again, that was two things, mutually exclusive and independence, all in one question. Okay, amigos, we are almost there. Finishing up our last lesson. I believe we've just got this table. What I would like you to do right now, hit pause. I would like you to fill this in and tell me if these are mutually exclusive or not mutually exclusive. You are going to put a massive star somewhere all around this page. If you understand this, I know what I'm doing. I'm ready. Hit pause. Come back to me in a couple minutes when you're done. Okay, friends, this is it. Let's see how you did. So, label as mutually exclusive or not mutually exclusive. Rolling 2 dice and getting a sum greater than 7 or a total less than 10. Well, that can happen at the same time. That's not mutually exclusive. That sounds like me getting, how about an 8? That's greater than 7 and less than 10. From a standard deck of cards, drawing a heart or a diamond. Well, that's mutually exclusive. They can't happen at the same time. From a standard deck of cards, drawing a jack or a spade. Not mutually exclusive. How about the jack of spades? Selecting marbles from 2 bags, selecting a red marble from 1 bag, and selecting a green marble from a 2nd bag. Well, that's mutually exclusive. They're 2 completely separate things. Here's bag 1, here's bag 2. Now, the next one here, my Venn diagram, do you remember this one from way back when? A couple of units ago? It depends on this question how we're viewing the sets. If we're looking simply at set of fruits and sets of veggies, sets of fruits and veggies are definitely mutually exclusive. However, if we're looking at these sets right here, if we're talking about whatever the heck set S is, why I called it S, I don't really know. S and F are not mutually exclusive. So F and S are not mutually exclusive, but F and V are. So it depends what we're looking at there. I didn't define it very well. Okay, over here, this is definitely mutually exclusive. That's the formula for mutually exclusive. Can't screw that one up. I hope. All right, almost there. This is not mutually exclusive. Again, that's the definition of not mutually exclusive. Here, there's an overlap, not mutually exclusive. There's people that are on yearbook club and student council. Do you remember that picture too? Recycling, I get lazy at the end of the year. I like to just use my same drawings over and over. Okay, last ones, which huge star here. Okay, show up. I guarantee you get this question on your diploma. So in a class of 32 students, 17 play guitar, 10 play the drums, 5 play nothing. Okay, well, I'm going to draw me a Venn diagram. So I've got 5 people that do nothing. There's 32 here. So what does it say? 17 play guitar and 10 play the drums. Right? Oh, wait a minute. I want to think about this. Look, I'm going to add these numbers up. 17 plus 10 is 27 plus 5. Oh, 5 play nothing. All 3 of those added together is 32. So guess what? I shouldn't have drawn it like that, should I? Good question. Guess what? These kids only play 1 instrument each. Mutually exclusive. So the next one, 35 kids at McDonald's work the fry machine, 20 cook hamburgers in quotations because there's no way those things are really hamburgers, and 10 make the shakes. Okay, well, if I add these numbers up, that's 65 people accounted for, but it says there's only 50 employees, so guess what? There's going to be an overlap. 15 people do more than something. There's an overlap. So Guess what? Not. That's the sloppiest N I've ever drawn in my life. That actually looks like a W, doesn't it? It looks like what? What? Mutually exclusive? What? Not mutually exclusive. Okay, that's it, amigos. You did it. You survived almost all of 30-2. Hope that was okay for you, and hope to see you soon.